Okay, Calc BC, Unit 2, Assignment 12, Office Hours. Some more L'Hopital's rule. I want to box your initial indeterminate form and you see other indeterminate forms along the way that justify your next steps. So a lot of these on the front are just sort of classic L'Hopital's rule problems, nothing weird like the ones we've been doing recently. Check your answers, pause it if you need to. These answers should also be online. I'll give you a second to check them. So answers on the back. Getting some more typical ones, 12, 13, 14, and then things start getting a little weird for the rest of them. Using some of our new techniques. Pause it if you need to, so you can check your answers. And here's the last ones. Pause it if you need to. Okay. All right. Let's see if we can do these. So right off the bat, we get 0 over 0, initial indeterminate form. We do L'Hopital's rule. X approaches 2. Derivative of the top, derivative of the bottom. The answer is 1/4. Done. Another way of doing this problem, just while we're talking about it, is this is a hole in the graph. So if you factor the top and bottom, the hole would go away, and you'd reevaluate it at the hole, and you would get 1/4 that way. So that's a different way of doing it, the way we first started talking about it. Number 2, if we just plug 0 in, we get 0 over 0. Now, the way we've been doing this is a special case. I don't know if you guys remember, where we make the sine of x over x. So, but we want the same thing inside. Now, there was a 2 here originally, so to get a 5 here, I got to multiply the top by 5 also. And then that goes to 1, and so our answer is 5/2. That's without L'Hopital's rule. Now, with L'Hopital's rule, I think it's just good right now to exercise all your options just to get good at this. It's going to be 5 cosine 5x over 2. Cosine of 0 is 1. Answer is 5/2. L'Hopital's might have been easier. Okay, here, plug 2 in. Square root of 4 is 2 minus 2 is 0 over 0. No other ways of doing this problem. Just L'Hopital's rule. And so this is going to be to the 1/2 power. It's going to be 1/2, 2 plus x, to the negative 1/2, to the bottom. Now if you plug, now I might clean this up. Just make it easier to think about. This is the same thing as 1 over 2 square root of 2 plus x. If you plug 2 into that, square root of 4 is 2 times 2 is 1/4. Okay, over here, cube root of 1 is 1 minus 1 is 0 over 0 in an initial indeterminate form. I want to think of this as a 1/3 power. L'Hopital's rule, 1/3 x to the negative 2/3 over that. I clean it up just to make it a little easier. This is the same thing as 1 over 3 x to the positive 2/3. Plug 1 in that, and you get 1/3. Okay. I guess, yeah, okay. I guess an alternative way of thinking of this problem is to think of this as the cube root of x cubed minus 1 cubed. So you could think of this as a hole in the graph, and you could do a difference of cubes, you could factor it. So just keeping your mind up. This would be a weird way of thinking of even doing it, but this is the difference of cubes technically. And then it would be x to the 2/3. And then be 1 squared is 1. And you multiply them together and you get the cube root of x. The same, opposite, always positive. That's the hole in the graph. So leaves a 1 on the top. And if you plug 1 into this, 1 to the 2/3 is 1, cube root of 1 is 1, plus 1 is 1, you get 1/3. So that's taking the hole out of the graph approach. Kind of interesting, weird. This one, cosine 0 is 1, so you can get 0 over 0. Initial indeterminate form. I think we just have to use L'Hopital's rule here. Derivative of the top is going to be positive sine x over 2x. If we plug 0 in, we get 0 over 0 again. So we're going to use the stronger form of L'Hopital's rule. And derivative of the top is going to be cosine x over 2. It's going to be 1/2. Next one, sine of pi over 2 is 1, so it's going to be 0 over cosine of pi is -1, so 0 over 0. So we can do L'Hopital's rule. Derivative of the top is going to be negative cosine. Derivative of the bottom is going to be negative 2 sine 2x, chain rule. Negatives cancel. Cosine of pi over 2 is 0. Sine of pi is 0. So I guess we're going to do it again. Negative sine x. I got rid of the negatives. Over 4 cosine 2x. Plug pi over 2 in here. Sine of pi over 2 is 1. So you get -1. Cosine of pi is -1. So we get positive 1/4. Okay. Number 7. Cosine 0 is 1, minus 1 is 0, over e to the 0 is 1, minus 0 minus 1 is 0. Initial indeterminate form. Derivative of the top. Derivative of the bottom. 0 over 0 again. L'Hopital's rule again. Negative cosine x over e to the x, which is going to be -1 over 1 is -1. Okay, next one. If we plug 2 in, we get 0 over 0. So we do L'Hopital's rule. This could be one that we can maybe take the whole out of. I feel like L'Hopital's rule is going to be the easier way of doing it. I'll probably try and show you the other way in a second. But get 0 over 0 again. 2 over 6x, and that's going to be 2 over 12 is 1/6. The other way of doing it is trying to factor the top and bottom. The top seems x minus 2x minus 2, which makes sense. You should expect an x minus 2 to come out of the top and the bottom since it's what's making everything go to 0. So I would do synthetic division, but I know I'm trying to take a 2 out. So I don't need to do Rashomon theorem. Let's see. Works out nice. Get a 0 at the end. So this is going to be x minus 2, x squared plus 2x minus 8. One of these cancels. Plug 2 back in. You get 0 over 0 again. So we should probably factor this more. X minus 2x plus 4. So there's another hole. So it's going to be 1 over that. Which is going to be 1 over 6. So it's another way of getting the same answer. I think that was a lot harder though. I think L'Hopital's rule was the way to go. This one will be 0 over 0. So we could do L'Hopital's rule. There is another option. I think L'Hopital's rule works pretty nice though. cosine of 0 is 1, so we just get 4/3 done. Otherwise, the other way, which I'm probably going to ask you guys to do some problems with L'Hopital's and some without on your next test anyway, so it might be good to get good at all these. Now, on these ones, I'm trying to get that pattern of sine of something over the same thing. So I want a 4x here and I want a 3x here. Now the x's take care of themselves, but to introduce a 4 here, I need another 4 on the top. To introduce 3 here, I need another 3 on the bottom. That goes to 1, that goes to 1. Answer goes to 4/3. So that's a work you would show without L'Hopital's rule. So that'd be good to get used to all these. Tangent is sine over cosine. That's going to be 0 over 0. With L'Hopital's rule, I'll show you without in a second. The tangent is secant squared, which is 1 over cosine squared, which is 1. Now, without L'Hopital's rule, you would break apart the sine and the cosine and say, well, that's going to 1, and that's going to be 1 over 1 is 1. So that's the answer without L'Hopital's rule. Got to be able to do both. Next one, 0 over 0. Now, this one I think we could do a whole, but I'll do L'Hopital's rule first. And take a derivative of the top, derivative of the bottom, maybe rewrite it. And we get 1 over 4. Otherwise, you could take the whole out, factor the top and the bottom. Now, the top I'm going to leave the way it is. The bottom, I'm going to act like it's a difference of squares. So square root of x minus 2, square root of x plus 2. And then these guys cancel each other out. Plug 4 into that, and you get 1/4. So that's how you do it without L'Hopital's rule. Like I said, you need to be able to do these multiple ways. I'm going to ask you to be able to do them multiple ways. Okay, let's see. Pi over 2, 1 over cosine. Cosine pi over 2 is 0. So that's going to be infinity over, this is sine over cosine. Sine pi over 2 is 1. Cosine of pi over 2 is 0. So you're going to get in division by 0 again. So it's the initial indeterminate form. And so we'll take the derivative of the top and the bottom. Secant is secant tan. Tangent is secant squared. Probably clean this up. This is sine over cosine. This is 1 over cosine, so the cosines cancel. It's a limit as x approaches pi over 2 of sine. The sine pi over 2 is 1. Otherwise, we probably could have did this without L'Hopital's rule by just simplifying the original problem and saying, okay, well, let's just change everything sine and cosine. Secant's 1 over cosine. Tangent sine over cosine. Multiply through by the least common denominator 2. So this is the non-L'Hopital's rule approach. Get cosine x plus 1 over sine x. If you plug pi over 2 in here, you get 1 over 1, which is 1. So there you go. 2 approaches. 13. This is going to infinity over infinity. We're going to take derivative of the top and bottom. Probably clean it up. I'll get rid of the complex fractions. Still get infinity over infinity. If we left it, we would have got 0 over 0. I had to do L'Hopital's rule again anyways. So we're going to have to do L'Hopital's rule again. I mean, you could look at the dominant terms because they're going to infinity. They're the same degree, so it's the ratio of the coefficients 1 over 1. Or if you do L'Hopital's rule again, you get 1. Okay, this one is going to be infinity over infinity. Without L'Hopital's rule, you just look at the dominant terms. They have the same degree, ratio of the coefficients. Answer is 5/7. That's without L'Hopital's rule. That's if you're going to infinity. But we could do L'Hopital's rule. We get infinity over infinity again. So we do it again. And the answer is 5/7, just like we said. Okay, next one's I'm getting to some of the interesting stuff. So this is going to be 0 plus times natural log. We just approach 0 is going to be negative infinity. So that's your initial indeterminate form. Our strategy is to change it to a fraction so we can get that indeterminate form. We're allowed to use L'Hopital's rule on. I would leave the ugly part on top and move the easier part on the bottom. So we get permission to use L'Hopital's rule now. I'd clean it up. And the answer is 0. Okay, all right. Next one. Tangent is sine over cosine, right? And it's going to 0. So sine is 0 over cosine is 0, which is 0. So it's going to be infinity times 0. So we want to get into a fraction. Now, we could do that, maybe. And here, we get 0 over 0. So then we can take the derivative of the top and bottom. So it's going to be secant squared times derivative of what's inside, which is negative 2 over x squared. Derivative of the bottom is negative 1 over x squared. So the x squareds cancel, the negatives cancel. Secant is 1 over cosine, right? So there's a 2 left. Don't forget that. Cosine of 0 is 1, so that's going to be 2 for our final answer. Okay. Next one, cosine is 1 over sine. Cotangent is cosine over sine. Right, so if you plug 0 plus in, it's approaching 0, so it's pos infinity minus pos infinity plus 0. The indeterminate form is really just infinity minus infinity. 0 doesn't really matter. So the strategy here was to combine them into a single fraction. So we need to think of them as fractions first, which we've already started doing. We need to get them least common denominator. So it's going to be sine x, 1 minus cosine x plus. Now here's the deal. This is what we could do. We could just think of this guy on its own. Just leave him on its own. I mean, you could bring him involved. It's going to get messier. I mean, you could. But you could just leave him on his own. This is easy. That's just going to 1. By the way, that's supposed to be a 1, actually. Sorry. But doesn't really make difference compared to infinities. So if we do this, cosine 0 is 1. That's going to be 0 over 0 plus 1. I guess I should have wrote that over here. So we're going to take the derivative of the top and bottom. The top's going to be sine x, derivative of the bottom's going to be cosine x, and we're just leaving this guy over here. We're not doing L'Hopital's rule on him. You could bring it into it, but it's not necessary. Sine of 0 is 0 over 1. 0 plus 1 is 1. Now, like I said, you could bring the cosine into it, and so instead you could have done this. 1 minus cosine x plus sine x cosine x all over sine x. You could do that. And then that would be 0 over 0. And you do L'Hopital's rule on the whole thing. So this is alternative. I think it's a little more complicated. The top's going to be sine x, and then you got to do product rule. So it's going to be negative sine x squared, and then cosine x squared over cosine x. So 0 in here would be 0 over 1. Sorry, let's see. 1 over 1 would be 1 that way also. Harder than necessary. All right, this next one is going to be infinity minus infinity. So we should... Ooh, this one's interesting. So they're not fractions. But what we're going to do is combine them into a single natural log using log rules. And then take the limit of the inside, which is infinity over infinity. Okay? And so then we'll just take we're going to essentially move the natural log out, which is properties of limits say that we can do this. And take the derivative of what's inside. That's going to give you 2. That's your final answer. So that's cool. I mean, so what we, yeah. I mean, I guess we could have taken the approach of kind of like we've done with the exponent problems, where you're like, well, something's stuck in the exponent. How do we do it? Well, something's stuck in the log. How do we deal with it? You could say, well, let's say this is the function. We want to get that stuff out of it. So how do you get stuff out of a log? You exponentiate it, right? And then we could take limit as x goes to infinity of e to the f of x, which is limit as x goes to infinity of 2x over x plus 1, which is infinity over infinity, which gives you limit as x goes to infinity of 2 over 1, which is 2. But then you have to re-log this function. So if you want the limit as x goes to infinity of the original function, you have to take the limit as x goes to infinity of natural log of e to the f of x, which is what we just found, and we get natural log of 2. So I guess that'd be a little more efficient way of doing it. 19, e0 is 1, so 1 to the infinity is your initial indeterminate form. So we're going to make a function. Got to get rid of that exponent, take natural log both sides. Take limit of that. Now we might want to just go ahead and think of this as a fraction, or maybe not. That's going to be infinity. Either 0 is 1. That's going to be 0. So I think if we think of it like this, we're going to get 0 over 0. Right? Just kind of jump into it being a fraction instead of trying to make it a fraction afterwards when it's pretty much almost a fraction. So as natural log approaches 1, it goes to 0 over 0. So now we could do L'Hopital's rule. 1 over the derivative, or the derivative of the top, 1 over what's inside times the derivative of what's inside. Chain rule. Put parentheses around it. Maybe clean it up. So we're going to get 2 over 1. Now we got to re-exponentiate it because we want the limit of the original function. So we need to take the e to the natural log of the function, which is what we just found. So it's going to be e to the 2, e squared. Don't forget to do that. Okay. 20. It's going to be 1 to the infinity. So similar issue. Got to get that exponent out. Then take the limit of this new function. That's going to be 0 over, so let's just think of it as a big fraction because we get 0 over 0. Okay, so we're going to do L'Hopital's rule. And that's going to give us 1. But we want the limit of the original function. E to the natural log of the f of x, which would be e to the 1, which is e. Okay, next one. It's going to be 0 to the 0. All right. Issue with exponents. We take the same approach each time. Take the natural log. Log rules. Take the limit. So we're going to get 0 times, let's see, 0 times natural log of 1 is 0. Oh, wait, natural log of 0 is going to be negative infinity. So we need to change it into a fraction. Leave the natural log on top. Unless you like making your life really much harder than it has to be. Now we get negative infinity over infinity. So we do L'Hopital's rule. One over x squared minus 2x plus 1 times derivative of what's inside, 2x minus 2. This is going to be negative 1 over, it's like there's a negative 1 on that, so x minus 1 squared. Now, we could try and clean this up a little bit to get rid of, no, that doesn't work. Okay, so I'm going to rewrite this as not a complex fraction anymore. So it's going to be negative 2x minus 1 cubed, if you factor that out. And then multiply by the reciprocal over x squared minus 2x plus 1. So that gives you 0 over 0. So we get to do it again. This is a fun one. Negative 6. Let's simplify this. Look, check that out. So now if we plug 1 in, we get 0 after all that. And then we need to re-exponentiate it. E to the 0 is, the final answer is 1. I'm kind of skipping some of the technical work I usually show just because I'm running out of room. Okay. This is going to be 0 to the 0. Natural log both sides. Log rules. Limit of the new expression. Okay, which gives you 0 times negative infinity. So we've got to change it to a fraction. At some point, you start to get really good at these, like me. I mean, Just getting the same kind of stuff over and over again. Now we do L'Hopital's rule. Maybe we could clean it up. Okay. This is gonna be 0 for 0. We gotta do L'Hopital's rule again. Gotta do product rule. Plug 0 in here. 0, 0, 0 over 1 is 0. Then you have to re-exponentiate. E to 0 is 1. Okay. Okay, last one. We're going to get 1 to infinity. F of x, natural log, log rules, limit of the new expression. Do we want to just go ahead and think of this as a fraction right now? Because that's going to go to 0. Yeah, let's just make that a big fraction. So that's going to be 0 over 0. So we do L'Hopital's rule. We could clean it up. Get rid of the complex fraction. And we get 0 over 1 is 0. So this is the way we technically usually do it. We want the limit as x approaches 0, superscript plus, what should be in your work, of the original function, which is going to come from the limit of e to the natural log of the original function, which is what we just found. Right? That's what that is. So it's going to be e to 0 is 1. Man, tired out. But hard work, got it done in about 30 minutes. Good practice. You should be getting, if anything, you should be getting really good at this and trying any other approaches you can whenever L'Hopital's rule could be avoided. But try and do both of them, because in your next test, I'm going to force you to use L'Hopital's rule in certain problems and force you to not use L'Hopital's rules in certain problems. And some of those problems can be done either way. So